Thanks, David, for the introduction, and thanks for the opportunity to speak here at ATARC. So let me share my screen. I've prepared a slide deck. Can you see my screen now?
Yes, we can.
And if I switch slides, is that working?
Beautiful.
Yes.
Excellent. Excellent. Thank you. All right, so let's get the kick started. So as Lily mentioned, I'm David. I'm the CEO and co-founder of SB Quantum. And at SB Quantum, we're all about magnetics. And our aim is to reveal what is invisible otherwise. And we are enhancing the current capabilities that are provided by classical technologies with quantum and the development of customized algorithms. So I'll quickly dive directly into the core of the topic, which is magnetic sensing. And I think it's a good example of how quantum sensing is nearing commercialization and how it fits into the whole existing ecosystem of classical sensors. So of course, magnetic fields are everywhere. The Earth magnetic field covers the whole planet. It affects or is affected by anything that is metallic or magnetic. But it turns out that the magnetics is a pretty messy business in general. The key question is, how do I distinguish an object that is going around me? It can be, for instance, a car, which will create a magnetic signature. How do I distinguish this from what I'm interested in measuring? Like, let's say, an ore body or a cobalt fault into the ground, which would be very relevant for the mining industry in the whole context of the electrification and the big demand for batteries going forward. So our goal at SB is to open up new opportunities using magnetics, and to achieve that, we go beyond what is typically used by the magnetics industry. So traditionally, scalar magnetometers are used. So here on the right, you can see the magnetic field map of a magnetic object, which is given by the dipole. So if you look far enough, everything looks like this. It looks like a dipole. So how can you extract more information about the magnetic phenomena around you? You can use vector magnetometers to get 3 additional quantities instead of 1. But the trade-off there is that if your vector magnetometer is moving through space, you're going to get a measurement change, which is not indicative of something interesting going on, but just a matter of the platform moving around. The most that you can extract from magnetic fields is by performing what is called tensor gradiometry, so measuring the gradients of the vector magnetic fields. And this forms the basis for what we call magnetic intelligence. So from reconstructing that whole matrix, you can customize interpretation algorithms, which will allow you to tell where is the object, what's its size, how it's oriented. And we're really leveraging that in order to better understand the magnetic environment. Ultimately, this provides 5 times more data as compared with scalar magnetometers. And as you'll see, for various applications, it can have a big interest. So to go there, we're building what we call the magnetic intelligence platform, which is composed of a platform to transport the sensors. We have developed a backpack system, but eventually we're looking to integrate into drone systems. We're fitting an array of vector magnetometers as required to perform magnetic intelligence. All that data is fed through an interface on which cleaning algorithms and interpretation algorithms are running. And the end result, so after distilling all the very complex and convoluted information about magnetic fields, all of that is fed onto a dashboard. So for some instances, it's only a marker on a map saying, okay, magnetic phenomena happen here. It's a car, it's at X distance moving at this speed. So really, with this platform, our goal is to really distill what matters for the customer. And really, quantum there can help, since everything is based on quantitative measurements of the magnetic field. So leveraging the properties of quantum with the vector allows you to get a very accurate performance of the algorithms. How does our solution stand out from classical and existing quantum technology? So magnetometers aren't a new technology. It's been used for decades for submarine detection initially, but it has evolved quite a bit over time. One of the most advanced magnetometer technology is the squid system, which requires cryogenics, so often at the liquid helium temperature. So here you have a kind of a surveying system that's used in geophysics, which is quite bulky. The trade-off there is that this technology provides relative readings. So it's not as useful for geological interpretations, or you have to be very careful in the way that you use it. And next, we have the Fluxier technology, which is based on coils, on induction, so classical technology. Being based on classical properties, it suffers from a thermal drift, so requires calibration from time to time. Really, if you exploit the quantum properties of atoms, you can go there to atomic vapor magnetometers, which is quite an established technology, quantum-based. So you have a very stable measurements. However, it provides only a single point of data, so only the amplitude of the magnetic field and not the vector, so you cannot tap into magnetic intelligence algorithm. So at SB, we're developing a diamond-based quantum magnetometer, which provides not only the amplitude of the magnetic field, but also the vector information, and in a way that is based on quantum properties of impurities in diamond. So that allows us to remove the drift and to reduce the calibration errors, and doesn't suffer from some of the trade-offs of classical technologies, such as dead zones or heading errors, which might be very critical for some of the end use cases. It's also a very compact sensor, so there's a big drive to move towards a drone deployed platform. So this sensor is fully compatible with these small and agile platforms. Currently, we're focusing on three key streams for which we believe that the quantum properties of the sensors can offer an advantage. First, one of them is mining, then we have defense and space. And here I put advantages in terms of the user needs, but also the technical requirements. It's very important to distinguish these two, because often when we come from academic background, we're often used to think in terms of technology driven, but there's really other considerations to be thought of. And this is where magnetic intelligence can provide value. So for mining, the goal ultimately, magnetometers have been used in exploration for decades. And the goal there is to provide data that makes geological sense so that we can guide the drilling process that is required in order to establish a mine. On the technical side of things, they want the best data quality, and they don't want cryogenics, which might be very cumbersome to deploy in the northern territories. For defense, their hope is that with the measurements, the magnetic field measurements, they can perform detection and classification. So really refining their understanding of the environment in ways that is not possible with conventional sensing technologies. The technical driver there is to have the most sensitive instruments so that you can detect, for instance, submarines at a very long distance. Lastly, for space, user requirements is really to measure what matters. So you want to measure the Earth magnetic field. You don't want to measure the magnetic field created by the satellite. So that implies that on the technical side, you need a very accurate measurement. So I'm going to go a bit deeper in each of these three domains. And just quickly describe what we see as being an advantage for quantum. So first of all, for geophysics, the goal is improve geological interpretations. The quantum advantage there is really the calibration efficiency. So since every measurement is based on the quantum properties of impurities and diamond, they can be easily recalibrated with the fundamental properties of the system. Accuracy is very important too, because when you get a baseline magnetic field map, you want to be able to compare it with pre-existing maps, or over the span of a few days or weeks, be able to compare your measurements together so that you can drive and refine your inversions, which are critically required to figure out the underground geology. So here you have a few examples of field trials that we've done, and the benchmarking of our magnetometer. For the defense, we've been most interested from the detection and classification domain. So on the left here, you have the reconstructed trajectory of a metallic object in 3D space using an array of vector magnetometers. So really coming back to that concept of magnetic intelligence. And we've applied these concepts for special operations awareness. So seeing through walls, seeing objects even though they're concealed or camouflaged, or even through smoke, through rain. So this is where magnetics can provide an information that might require otherwise a combination of multiple sensors. And really with magnetic intelligence, we can reconstruct the trajectory, the distance, the object size and speed. And the key challenge there is to minimize the magnetic interference, and this is what we can achieve with magnetic intelligence. Our end goal so far, we have developed a backpack equipment for the special forces. Our end goal is to put that backpack into a handheld device on the long run, and this is one of the key advantages that we see with the quantum, the enhanced capabilities in terms of miniaturization. Lastly, I want to mention the space track that we're pursuing. So we're involved into the NASA MagQuest challenge to refine the world magnetic model with quantum sensing. So that world magnetic model is in every navigation system. GPS tells you where you are, but it doesn't tell you which way you're pointing. So every time you take your cell phone, look at that blue arrow, it's comparing the magnetometers in your cell phone with the worldwide magnetic map. So we are currently fitting our quantum magnetometer into a CubeSat. This is in collaboration with Aspire in the UK, and adapting customized magnetic installation algorithms in order to screen out the magnetic interference that the satellite will create. So this is a big ongoing effort, and in the second quarter of 2023, we're going to go through independent evaluation by NASA to make sure that we're measuring the right field up to 1 nanotesla accuracy, which is 1 over 50 millionth time the Earth's magnetic field. So that's quite a challenge. All right, I want to say a few words on the diamond magnetometer. How does it work? Well, at a very high level, it's based on impurities in diamonds, so substitutional nitrogen atom by the side of a vacancy, and that frees up electrons. The electrons have the quantum property of spin that is very sensitive to a magnetic field. You can think of it in terms of the smallest magnet that you can find. And the way that we initialize and read out the system is using a green laser pulse. So here you can see a green laser pulse going on a chunk of diamond in which there's millions and millions of these impurities. And following that excitation, it will re-emit a red glow that is even visible by the naked eye. And all the information about the magnetic field is encoded into the amplitude of that signal and of the frequency at which we will begin to induce and manipulate these spins. So currently we are commissioning our first release of a magnetometer for field deployment. So We have, since the onset, we have focused on commercial off-the-shelf integration components in order to make a magnetometer that we can bring to the field. Our objective is to be sub-nanotesla in sensitivity and in accuracy. And as I mentioned, this is quite a challenge since this is 1/50 million times the Earth's magnetic field. So to get there, we're really leveraging collaborations, mainly in Canada for now. And so we have ongoing collaboration with McGill University, with the NRC, and Institut Quantique at the University of Sherbrooke to look at the different level of TRLs research to enhance the performance of our device. And the way that we look about collaborations, and I think this is a key point in developing quantum sensing technology. So there's plenty of classical sensors that work perfectly well, and you need really to leverage the experience of the vast community working on these topics. So our approach to collaborate and to accelerate the development is to provide the demonstration units to key stakeholders, provide remote access even to the devices so that people can learn a bit more about quantum, apply some of their novel ideas. And one of the success that we've had is partnering with Keysight Technologies in order to provide what we call a demonstrator unit, which interfaces with their quantum electronics control platform. So this is a platform on which we can customize any control, quantum control, or readout pulse sequences in order to explore novel ideas and really to move towards the ultimate limit of quantum sensing, which is provided by the Heisenberg limit. And what it means is that we could ultimately enhance the sensitivity by a factor of square root of n. And since n here is the number of quantum systems that we're probing. In our case, it's in the millions, in the billions range. So eventually, this is far from being done. It's a very low TRL works that's been accomplished, that's being accomplished all around the world. Ultimately, what quantum could provide is an enhancement up to, let's say, 1,000 on the sensitivity. So really by using the advanced control capabilities, readout capabilities of these quantum systems, we can really achieve more than what's available classically. So that's it. That's what I had to present about the SB Quanta and our ongoing challenges on quantum sensing using diamonds. So the floor is open for questions. Yeah, thank you.
Thank you, David. Any questions?
All right. Are there any questions for anyone? Really for David? Okay.
I have a question, actually. Sure. So you mentioned about this method can minimize magnetic interference. So this is kind of the comparison is with the classical method or device, right?
Yes, so these same concepts can be applied with quantum sensors. However, you might get diminishing returns since the classical sensors can drift over time, which is something in an unpredictable fashion, which is something that the algorithms might not be able to understand.
Okay, thank you. Any other questions?
Someone in the chat said, hi, nice talk. I'd like to ask how it is with the range versus spatial resolution. They're usually anti-correlated. Great. I guess it is important for space application.
Okay, yeah, good question. So of course, when you're performing magnetic sensing from space, You get very little resolution on the magnetic phenomena, not as much as you would surveying on the ground. And so really, when you're looking from space, it's about describing the magnetic core of the Earth. And then you can adapt a model and describe with maybe 1,000-kilometer resolution how the field fluctuates through the Earth. So this is still very useful for navigation purposes because you can kind of abstract what the local disparities that there might be. So of course, with the 1 over the distance cubed dependency of magnetic fields, like there's so much you can achieve from space. But on the ground, if you go with an array of vector magnetometers to perform magnetic intelligence, then since you're measuring the gradients of magnetic fields, you can even refine smaller features into the ground. So yeah, that would enhance the accuracy.
Allison said, thanks, David. How would you want to see better engagement with government?
Great. So we're big fans of open innovation programs. So actually, the MagQuest program we found by challenge programs from the National Geointelligence Agency. So we see this as a very good way, especially for emerging quantum sensing companies, to get in direct contact with very specific problems and develop their solution around that. So for us, it has been very successful. And yeah, from across the domains, it could be very surprising what the quantum sensing can offer. So yeah, this is probably a way that would enhance and bring more agility to dealing with the government.
Awesome. Okay, that was all the questions in the chat. Does anybody have anything else that they want to bring up or ask or anything like that from David? We have a few minutes left. Okay. Well, then thank you so much for your presentation today, David. You did a great job. If anybody does have questions, please feel free to either email myself or Lily or Allison, and we will connect you and kind of get those squared away. But outside of that, everybody, you can have 5 minutes back of your day. And again, thank you, David.
Thanks.
Thank you.